Picture this. It's 1966, and a race car just made the entire motorsport world obsolete in a single lap. Not through more horsepower, not through better tires, through an idea so radical, so devastatingly effective that the entire global racing establishment did something they'd never done before. They didn't try to copy it, they didn't try to beat it, they banned it completely, permanently. And nearly 60 years later, that ban still stands. This is legacy motoring, and I spend way too much time thinking about the aerodynamic innovations that changed motorsport forever. If you're someone who loves the deep engineering stories behind racing's greatest machines, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Here's the thing. Most people who talk about the Chaparral 2E focus on the wing. The big, dramatic, barn door wing sitting high above the rear of the car like some mechanical creature spreading its wings for the first time. And yeah, the wing is incredible, but that's actually missing the real story. The real story is about a soft-spoken engineer from Midland, Texas, who understood something that Ferrari, Lotus, McLaren, and every other racing team on the planet had completely missed. And when he proved his point at 160 miles per hour in front of the entire racing world, the sport had an identity crisis. It's never fully recovered from. To understand why the Chaparral 2E hit the racing world like a freight train, you have to understand what racing actually looked like in the mid-1960s. Look, this was an era of raw, brutal, magnificent excess. Ford and Ferrari were spending what would be hundreds of millions in today's money to win Le Mans. Lotus was reinventing chassis construction. McLaren was rising as a genuine force in Can-Am racing. The sport had never been more competitive, more dangerous, or more innovative. But here's what most people don't realize about that era. All of that innovation, all of those millions of dollars and thousands of engineering hours were focused almost entirely on two things: more power and less weight. That was the formula. Want to go faster? Bore out the engine. Want to handle better? Strip everything that isn't essential. Aerodynamics was something airplane people worried about. In racing, it was an afterthought at best. Sure, teams had noticed that certain shapes seemed more stable at high speeds. Ferrari had started bolting small spoilers onto some of their cars. Lotus designer Colin Chapman had figured out that angling the nose downward helped with high-speed stability. But these were band-aid solutions, intuitive guesses, rather than engineered solutions. Nobody truly understood the relationship between airflow, pressure differentials, and vertical force acting on a race car. Wind tunnels were for aerospace companies. Computational fluid dynamics wouldn't exist for another 2 decades. If you wanted to test an aerodynamic theory in 1966 racing, you built the part, bolted it on, and found out the expensive way whether it worked. The prevailing wisdom was so deeply embedded in the culture that questioning it was almost career suicide. More power, less weight. Brave driver. That was racing. That was always racing. That was going to be racing forever. Except in Midland, Texas, someone hadn't gotten that memo. Jim Hall was not your typical racing entrepreneur. While most team owners came from the ranks of wealthy enthusiasts or former drivers who'd cashed out successfully, Hall came armed with something genuinely dangerous in any competitive field: a Caltech mechanical engineering degree and an obsessive need to understand why things worked, not just that they worked. He grasped fluid dynamics at a mathematical level. He understood pressure differentials and their relationship to vertical force. He could actually calculate what happened to air as it moved over and under a vehicle at racing speeds. Hall's company, Chaparral Cars, had already built a reputation for thinking differently. They were racing automatic transmissions in road racing when everyone else thought that was insane. They pioneered fiberglass monocoque construction while competitors were still welding steel tubes together. Every time the establishment said something couldn't be done, Chaparral had a habit of doing it anyway. But what Hall was sketching out for 1966 made all of those previous innovations look conservative by comparison. The problem Hall had identified was one of those beautifully simple engineering dilemmas that sounds obvious the moment someone articulates it, but that nobody had bothered to articulate before. Race cars need maximum downforce in corners. That extra grip, that invisible force pressing the tires into the asphalt, is the difference between carrying 90 miles per hour through a sweeper and carrying 120. It's the difference between slow and fast, and in racing, that's the only difference that matters. But here's the brutal compromise every team faced. That same downforce that makes your car a cornering machine becomes your worst enemy on a straight. Downforce means drag. Drag means slower top speeds. A car setup with a high downforce configuration for a technical circuit would get absolutely murdered on the long straights of a faster track. Every team was trapped in this compromise, constantly searching for the middle ground between corner speed and straight line pace. Now you might be thinking, well, everyone faced the same compromise, so it evened out. And you'd be right. That's exactly what Hall recognized. Everyone was trapped in the same box. The question he started asking was simple but revolutionary. What if you didn't have to stay in the box? What if the car could have massive downforce when you actually needed it, in the corners, and minimal drag when you didn't, on the straights? What if those aerodynamic characteristics weren't fixed parameters baked into the car's design, but variables that could be adjusted in real time by the driver at racing speeds? The answer, Hall realized, had been flying overhead for decades. Aircraft had solved this exact problem. Flaps, ailerons, elevators, all movable control surfaces that changed a wing's aerodynamic characteristics depending on what the pilot needed at any given moment. Maximum lift for takeoff and landing, minimum drag for efficient cruise. The technology existed. The engineering principles were proven. Nobody had simply thought to apply them to a race car before. Hall's solution was the movable rear wing, though describing it that way almost trivializes what he actually built. This wasn't a spoiler or a modest aero aid. This was a nearly 6-foot-wide aluminum wing mounted on twin struts above the rear of the car, capable of pivoting through a dramatic range of angles on command. At its maximum angle of attack, racing terminology for the wing's angle relative to the incoming airflow, it generated approximately 240 pounds of downforce at 100 miles per hour. At 150 miles per hour, that number climbed to over 500 pounds. Let me put that in perspective for a moment because those numbers can sound abstract. 500 pounds of downforce is roughly equivalent to dropping 3 professional NFL linemen onto your rear wheels simultaneously. It's the difference between tires barely maintaining contact with the track and tires being absolutely mechanically forced into the asphalt. In 1966, most cars at those speeds were generating lift, meaning they were literally trying to become airplanes. Hall's car did the exact opposite. But here's where it gets really interesting. The wing itself was only half the genius. The control system was the other half, and it was an absolute masterpiece of mechanical engineering intuition. Hall connected the wing directly to the brake pedal through a mechanical linkage. When the driver touched the brakes, the wing automatically rotated to its maximum angle, creating massive downforce and aerodynamic drag simultaneously. The car slowed dramatically without the driver needing to stand on the brake pedal with maximum force, preserving the brakes for when they were critically needed. When the driver got back on the throttle, the wing flattened to its minimum angle, reducing drag for full straight-line acceleration. Think about what this actually meant in practice. A driver approaching a fast corner at 160 miles per hour could simply lift slightly and touch the brakes. The wing responded instantly, pressing 500 additional pounds onto the rear wheels, slowing the car rapidly while simultaneously increasing rear grip for the corner entry. The driver could carry more speed into the corner than would ever be possible with conventional aerodynamics because they had forces working for them that simply didn't exist on any other car. Then, powering out of the corner, the wing flattened and the car accelerated without the drag penalty that a fixed high downforce setup would have imposed. The engineering challenges involved in actually building this system were staggering. The forces acting on the wing at maximum deflection and high speed weren't just large, they were trying to actively destroy the car. At 150 miles per hour with the wing at full angle, the drag force attempting to rip the assembly off the car exceeded 300 pounds. The downforce loads were being transmitted through the struts and into the chassis at angles and magnitudes that had never been engineered for in a road racing car before. Hall used aircraft-grade aluminum for the structural components, with wall thicknesses calculated to handle 5 times the maximum expected load. The pivot bearings were sourced from helicopter rotor assemblies, components designed to handle the kind of cyclic loading that destroys normal hardware. Every fastener was safety wired. Every weld was inspected. Every component was overbuilt because at 150 miles per hour, you absolutely cannot afford to discover that something wasn't strong enough. The mechanical linkage connecting the brake pedal to the wing was itself a precision engineering exercise. It had to translate the linear motion of pedal travel into smooth, predictable rotational motion of the wing without any delay, slop, or inconsistency. Hull used a system of bell cranks and push rods, the same basic architecture used in aircraft flight controls, because aircraft engineers had spent decades figuring out how to make exactly this kind of control linkage work reliably under severe conditions. Hull also understood something that many engineers miss when they're excited about a new idea: aerodynamic balance. Adding 500 pounds of downforce to the rear of a car without addressing the front is a recipe for disaster. The front end goes light, steering response disappears, and you've transformed the race car into an unguided projectile. So the 2E featured carefully designed front aerodynamics as well, channeled air under the nose, creating a low-pressure zone that generated proportional front downforce as speeds increased. It wasn't adjustable, but it didn't need to be. The ratios were calculated to maintain balance throughout the car's operating speed range. Powering all of this aerodynamic sophistication was a 410.7 cubic inch Chevrolet V8 producing approximately 520 horsepower, mated to one of Chaparral's signature 3-speed automatic transmissions. That automatic wasn't laziness or compromise. It was deliberate. It kept both of the driver's hands on the wheel at all times, which, with an active aerodynamic system to monitor and a car capable of generating previously impossible cornering forces, was genuinely important. While other drivers were wrestling with manual gear changes through high-speed corners, Chaparral drivers could focus entirely on the racing line and managing those revolutionary aerodynamic forces. The complete car weighed just under 1,650 pounds dry. Remarkably, impressively light when you consider it was carrying that entire wing assembly plus all of its associated hardware. The suspension used unequal length A-arms all around with carefully calculated spring rates that could handle the massively increased wheel loads without compromising the car's dynamic behavior. When Hull rolled the 2E out for its first test sessions at Rattlesnake Raceway, his private test facility outside Midland, even members of his own team had doubts. The wing looked absolutely absurd. It looked like someone had bolted a barn door to the back of a perfectly good race car as some kind of elaborate joke. Word spread through the racing community quickly, as it always does, and the reaction from competitors ranged from polite skepticism to outright mockery. One Ferrari engineer who saw photographs of the car reportedly said it looked like a shopping cart that had mated with an airplane. People laughed, openly, confidently, and completely wrong. The testing data told a completely different story. Lap after lap at Rattlesnake, the numbers coming back were almost difficult to believe. The car was posting times that shouldn't have been possible given its power output. The brake temperatures were dramatically lower than expected because the wing was doing so much of the deceleration work. Tire wear was more even and predictable. The driver feedback was extraordinary. The car felt, according to those early test sessions, like nothing else that had ever existed on four wheels. Hull brought in Phil Hill to drive the 2E at its first public appearance, a decision that in retrospect looks almost theatrical in its perfection. Hill was no ordinary hired driver. He was the 1961 Formula One world champion, one of the most respected and analytically precise drivers in the entire sport. He was also a man with a degree in automotive engineering, someone who could give detailed technical feedback rather than just telling you the car was fast. His opinion carried enormous weight in racing circles. When Phil Hill said something was good, people listened. The venue was Bridgehampton, a fast-flowing circuit on Long Island in New York during the September 1966 Can-Am round. The racing establishment had gathered, as it always did for Can-Am events, because this was the series where serious money met serious technology. McLaren was there, Lola was there, Ferrari-backed machinery was present. The fastest sports cars on the planet had assembled on Long Island for what everyone expected to be a competitive race between established powers. Nobody expected what actually happened. Hill's first flying lap produced an almost comical reaction in the pit lane. Track marshals were radioing in confused reports. Other drivers were asking their engineers what was happening with the white car. Crew chiefs were staring at their stopwatches and then staring at them again because the numbers couldn't be right. Hill wasn't just faster. He was faster in ways that defied the existing logic of race car performance. He was carrying speeds into corners that were simply not achievable with conventional downforce levels. He was braking later than anyone thought possible while the car remained completely stable. He was powering out of corners sooner and harder because the grip levels under acceleration were beyond anything the competition could match. And perhaps most visually striking of all, you could actually see the wing working. Watch footage of that first appearance and you can see the wing snap upward as Hill touches the brakes and flatten back down as he gets on the power. It's mechanical ballet at racing speed. The lap times were devastating. Hill was posting laps 2 to 3 seconds faster than anything else on the circuit. Now, here's something important to understand about what that actually means in the context of racing. A half-second advantage in modern Formula One is considered a massive gap. Teams spent hundreds of millions of dollars chasing half seconds. A full second advantage is the kind of thing that makes engineers question their careers. 2 to 3 seconds is not racing. 2 to 3 seconds is one category of performance, competing against a completely different category of performance. It's like bringing a current smartphone to a 1980s computer convention and asking why everyone else seems slow. The race itself became a demonstration rather than a competition. Hill didn't just win, he lapped the entire field, multiple times. He was so far ahead that the race effectively became a separate event happening between other cars for second place, while Hill drove at his own pace in a parallel universe of performance. The wing wasn't just providing faster corner speeds, it was changing the fundamental architecture of how a lap time was built. Brake zones were shorter because the wing did deceleration work. Corner speeds were higher because grip levels were unprecedented. Acceleration zones were longer and more aggressive because the wing provided extra rear traction on exit. The racing world went into something between panic and fury. Ferrari, which had never been particularly comfortable with anyone else being the most innovative team in the paddock, immediately redirected engineering resources toward movable aerodynamic research. McLaren began intensive wind tunnel work. Colin Chapman, who had built his entire career on being the cleverest man in any room he entered, reportedly spent 3 consecutive days sketching aerodynamic concepts. Teams that had been laughing at photographs of the 2E just weeks earlier were now desperately trying to understand how they could build something similar before the next race. Here's what most people don't realize about that moment. The 2E's impact wasn't just about the lap time advantage. It was about what the lap time advantage revealed. It showed that the entire competitive framework of racing, the assumption that everyone was more or less working with the same fundamental tools and that small gains in power or weight would determine the hierarchy, was completely wrong. Hall hadn't found a better way to do what everyone else was doing. He found a completely different thing to do. And that distinction matters enormously. The Can-Am series continued through the 1966 season and into 1967, and the 2E's dominance remained essentially unchallenged. At Laguna Seca, the car was timed through the famous corkscrew section at nearly 50 miles per hour, faster than the second quickest competitor through that specific complex. Let that land for a moment. Not 5 miles per hour, not 10. 50 miles per hour through one of the most technically demanding corner sequences in American road racing. That's not an aerodynamic advantage. That's a different physics equation. The data Hall was accumulating during this period was extraordinary in its scope and its implications. He had pressure sensors installed at multiple points on the car, primitive by modern standards but revolutionary for the era. The numbers they returned were things no road racing engineer had ever seen before. At maximum wing angle and 120 miles per hour, the additional load being pressed onto the rear contact patches exceeded 800 pounds. The car was generating lateral acceleration figures approaching 1.4 G in high-speed corners, numbers that wouldn't become routine in Formula One for another 10 to 15 years. But here's where the story takes its most fascinating turn. Because the 2E's success didn't just create a technical crisis in racing, it created a philosophical one. And that philosophical crisis, more than any regulation or technical challenge, is what ultimately determined the car's fate. Racing in 1966 operated under a set of assumptions so deeply embedded they were almost never articulated because they didn't need to be. Everyone understood intuitively that racing was about drivers. Yes, equipment mattered. Yes, engineering mattered. But the romantic core of the sport, the thing that made people care, was the idea that the bravest, most skilled human being behind the wheel would ultimately prevail. The machine was a tool, the driver was the story. The 2E complicated that narrative in deeply uncomfortable ways. When Phil Hill was 2 to 3 seconds faster than the entire field, was that Hill's genius? His bravery? His skill? Or was it Jim Hall's engineering? The honest answer, and this is what made people so uncomfortable, was that it was almost entirely Hall's engineering. A competent driver in the 2E would beat a brilliant driver in a conventional car. The machine had become so dominant that it had effectively marginalized the human element that gave racing its emotional core. Enzo Ferrari, a man who had spent his entire life pursuing any advantage he could find and had never shown the slightest hesitation about spending whatever it took to win, publicly called the movable wing concept a perversion of the sporting spirit. That is an almost breathtakingly hypocritical position from one of the sport's most ruthless competitors. But it also reveals something genuine about the anxiety the 2E had produced. If Ferrari of all people was appealing a sporting tradition to argue against a faster car, something had fundamentally shifted in how people were thinking about what racing was supposed to be. Other teams filed protests. Regulations were examined, word by word, by teams of lawyers looking for any provision that could be used to restrict the wing. The problem, legally speaking, was that Hall had broken no rules. The rulebook said nothing about movable aerodynamic devices. It didn't say anything because nobody had imagined such a device was possible. Writing a rule against movable wings in 1965 would have been like writing a rule against teleportation. Why regulate something that exists only in science fiction? The Can-Am series had built its entire identity around minimal regulation. Run what you brung was practically the series' motto. The philosophy was that unfettered innovation produced the most exciting racing and pushed automotive technology forward in ways that benefited everyone. It had worked brilliantly for years, producing some of the most extraordinary machines ever to race on public roads. But that philosophy had an implicit assumption buried inside it. That innovation would happen incrementally, that no single idea would be so dominant that it rendered the entire competitive framework meaningless. The 2E had violated that assumption so completely that the series faced an existential question. If you allow movable aerodynamics, you effectively mandate them. Any team that doesn't develop a similar system immediately becomes uncompetitive. The cost and engineering complexity of developing effective movable aerodynamics was beyond most teams. So open regulations, which were supposed to democratize innovation, would actually consolidate performance advantage in the hands of whoever solved the movable aerodynamics problem most effectively, which at that moment was one team, Chaparral. The pressure mounted from every direction simultaneously. Competitors threatened to withdraw from events. Sponsors who needed competitive racing to justify their investment raised concerns about the lack of genuine competition. Broadcasting partners worried that races had become processional. Even some fans, remarkably, complained that the 2E was making racing boring by being too good. Imagine the position racing had reached. A car so fast that people wanted it gone because it was winning too convincingly. By late 1967, the regulatory response was being coordinated at the highest levels of international motorsport. The FIA, the body that governs Formula One and most major international racing categories, announced that movable aerodynamic devices would be prohibited from all sanctioned competition beginning with the 1968 season. The language of the ban was precise and clearly written with the 2E in mind. Any aerodynamic device capable of changing its characteristics while the vehicle is in motion is prohibited. Clean, comprehensive, unambiguous. American series followed suit in rapid succession. The Can-Am held out briefly, consistent with its independent spirit, but even they eventually recognized that without the ban they would have no meaningful competition to offer. Within 18 months of the 2E's debut, its central innovation was illegal in virtually every form of organized motorsport on the planet. Hall had created something so devastatingly effective that the entire global racing establishment had united to eliminate it. Think about what that actually means for a moment. Not one governing body, not one series. Every major racing organization on Earth simultaneously decided that this one technology was too good to be allowed to exist. In the entire history of motorsport, that has essentially never happened before or since. Technologies get restricted, regulated, refined into acceptable forms. They don't get universally banned across every category simultaneously within 18 months of their introduction. The Chaparral 2E didn't just win races, it won so completely that winning itself became the problem. But here's the thing about banning a technology. You can make it illegal. You absolutely cannot make it forgotten. The immediate aftermath of the movable wing ban produced one of the most fascinating chain reactions in the history of engineering. Because the moment teams understood they couldn't have movable aerodynamics, every single one of them redirected that energy and anxiety into making fixed aerodynamics as effective as humanly possible. If the wing couldn't move, it better be generating maximum possible downforce at every point in its fixed position. If you couldn't optimize for both corners and straights simultaneously, you'd better find a fixed configuration that compromises little as possible between the two demands. The 1968 and 1969 racing seasons produced an almost immediate visual transformation in race cars that's genuinely startling when you look at the photographic record. Cars that had raced in 1966 with clean, smooth bodywork and perhaps a modest spoiler were replaced almost overnight by machines festooned with wings, fins, dams, and aerodynamic appendages that made the 2E's single wing look modest by comparison. The 1969 Formula One season in particular became almost comical in its aerodynamic excess. Wings grew taller and taller, mounted on increasingly spindly struts, reaching heights that blocked drivers' rear visibility and created structural loads that the cars weren't remotely designed to handle. That same 1969 season produced one of Formula One's most dangerous periods, when multiple high-speed wing failures caused serious accidents. The wings weren't failing because the concept was wrong. They were failing because teams were rushing to extract maximum downforce from fixed structures using materials and mounting solutions that hadn't been properly engineered for the loads involved. In a profound irony, the fixed wings that replaced Hall's movable system were initially far more dangerous than the movable wing had ever been, precisely because they were trying to do everything the movable wing did without the movable wing's ability to manage its own loads intelligently. Here's what most people don't realize about that transition period. The data Hall had generated with the 2E, the pressure measurements, force calculations, balance equations, and driver feedback that his team had meticulously recorded effectively became the foundation document for modern racing aerodynamics. His team's work proved, with real-world evidence rather than theoretical models, that substantial aerodynamic downforce was not only possible on a road racing car, but was transformative in its effects on performance. Before the 2E, teams were still debating whether aerodynamics really mattered that much. After the 2Es, that debate was permanently closed. Wind tunnels, which had been exclusively the domain of aerospace manufacturers and research institutions, began appearing at racing facilities within a few years of the 2Es' dominance. The profession of racing aerodynamicist, a job title that had essentially not existed in 1966, became one of the most sought-after technical roles in motorsport within a decade. Universities began offering courses in vehicle aerodynamics. Research papers were published. The entire scientific infrastructure of understanding how air interacts with racing cars at speed was built in the years following the 2E's brief competitive career. Look at a modern Formula One car and trace its aerodynamic lineage backwards through history. The multi-element front wings with their complex cascades and turning vanes, the carefully sculpted barge boards directing airflow around the side pods, the diffusers creating low-pressure zones under the car, the rear wing end plates managing vortex behavior. Every single one of these elements exists because of the questions that the 2E forced engineers to ask. How do you generate maximum downforce from a fixed structure? How do you minimize drag while maintaining that downforce? How do you ensure aerodynamic balance across a range of speeds? These questions are Hall's legacy, asked and answered billions of times over in wind tunnels and computational fluid dynamics simulations around the world every single day. The numbers involved in modern Formula One aerodynamics would be almost incomprehensible to the engineers who raced against the 2E in 1966. Current Formula One cars generate in excess of 5,000 pounds of downforce at maximum speed. That's 2.5 tons of invisible force pressing the car into the track. It's enough downforce, as the famous statistic goes, that a Formula One car could theoretically drive upside down on the ceiling of a tunnel at highway speeds. The tires experience loads that would have seemed like fantasy to a 1960s racing engineer. The lateral acceleration in high-speed corners routinely exceeds 5G, meaning drivers experience forces on their bodies equivalent to 5 times their own body weight sustained for multiple seconds at a time. All of that, every pound of it, traces its conceptual DNA back to Jim Hall's barn door wing generating 500 pounds of downforce in a Texas workshop in 1965. This is where it gets really interesting, because the impact of the 2E extended far beyond the racing world in ways that are genuinely underappreciated, even by people who know the car's story well. The automotive industry at large was watching what Hall was doing, not just the racing community. Engineers of production car companies understood that if aerodynamic downforce could transform a race car's capabilities this dramatically, it had implications for high-performance road cars as well. The development of performance road car aerodynamics through the 1970s, 1980s, and beyond follows a trajectory that is directly influenced by what Hall demonstrated. The Porsche 911 Turbo's famous whale-tail spoiler, introduced in 1975, was a direct response to the understanding of downforce that Hall's work had popularized. Ferrari's evolution of rear aerodynamics through their Berlinetta models of the 1970s showed the influence clearly. Every manufacturer building serious performance cars was now thinking about downforce as a fundamental engineering parameter rather than an aesthetic afterthought. By the 1980s, the influence had reached production sports cars more broadly. Manufacturers began understanding that aerodynamic downforce wasn't just a racing concern. At the speeds their cars were capable of reaching, managing the forces that air exerted on the vehicle was a genuine engineering necessity for both performance and safety. Lift, the phenomenon that makes cars feel progressively lighter and less stable at very high speeds, was being engineered out of production vehicles using principles that Hall had proven on track. Today, the legacy is everywhere if you know where to look. When a Bugatti Chiron deploys its active air brake at speeds above 250 miles per hour, slowing the car with aerodynamic force rather than mechanical friction alone, it's executing Hall's fundamental insight with 21st century technology. When a McLaren P1 or a Ferrari LaFerrari, a Zoperari adjusts its rear wing position for different driving modes, moving between low drag configuration for straight line speed and high downforce configuration for maximum cornering grip, it's doing exactly what Hall's wing did in 1966. The only difference is that these are road cars, where the movable wing band doesn't apply, and that the systems are actuated electronically rather than mechanically. And here's the genuinely fascinating regulatory wrinkle in all of this. Formula One, which banned movable aerodynamics comprehensively in 1968, introduced the drag reduction system, universally known as DRS, in 2011. DRS allows drivers to open a flap in the rear wing on designated straight sections of the circuit when they're within 1 second of the car ahead, reducing drag and enabling overtaking. It is, by any honest definition, a movable aerodynamic device. It changes the car's aerodynamic characteristics while the car is in motion. It does exactly what the regulations written in response to the 2E were designed to prevent. Now you might be thinking, well, DRS is clearly different because it's tightly restricted, only usable in specific zones, only when within a second of another car, and it provides a much smaller performance delta than Hall's wing. And that's all true, but the principle is identical. The sport banned movable aerodynamics absolutely, and then 43 years later, quietly reintroduced a tightly controlled version of the same concept because it needed the performance manipulation to manufacture the overtaking that fully optimized fixed aerodynamics had made nearly impossible. The irony is almost too perfect to be fictional. Here's what most people don't realize about where the technology might have gone if it hadn't been banned. Hall himself has spoken in interviews about the concepts he was developing when the regulations shut down the program. The 2E was, in his own framing, a first-generation solution to the movable aerodynamics problem. He understood its limitations. The wing was large and created significant drag even in its low-angle position. It was a single surface with a single axis of movement. The mechanical linkage connecting it to the brake pedal was effective, but crude compared to what an electronically controlled system could do. Hall's second-generation concepts involved multiple movable surfaces working in coordination. Not just a rear wing, but front elements as well. All adjustable, all working together to optimize the complete aerodynamic balance of the car for each specific section of track. He envisioned systems sophisticated enough to change configuration not just between corners and straights, but through the arc of each individual corner, adding more downforce as the car turned and reducing it progressively as the car straightened and accelerated. In essence, he was imagining what would today be called active aerodynamics, the kind of system that aerospace uses routinely and that road car manufacturers now deploy on their most advanced products. The drivers who actually raced the 2E describe the experience in terms that go beyond technical performance metrics. Phil Hill, whose career included some of the fastest and most dangerous cars ever built, including the terrifying Ferrari 250 Testarossa prototypes of the late 1950s, said the 2E gave him a feeling of confidence he'd never experienced in any other race car. Not because it was easier to drive in the conventional sense, but because it responded to what he needed in a way that conventional cars couldn't. When he needed the car to slow down and stick, it slowed down and stuck. When he needed it to accelerate cleanly, it cleared its aerodynamic decks and accelerated. The car felt, he said, almost intelligent, like it understood what he was trying to do. That description is striking because it anticipates by decades the design philosophy that dominates modern high-performance vehicle development. The idea that the best performance car isn't necessarily the one with the most raw capability, but the one that most intelligently translates driver intent into vehicle behavior. Active suspension, electronic stability systems, torque vectoring, adaptive aerodynamics, and modern road cars, all of these technologies share the same philosophical DNA as Hall's movable wing. They exist to give the driver access to the car's full capability by managing forces that would otherwise be beyond human reaction speed to control. The Chaparral 2E was banned for being too good, but in being banned, it planted seeds that grew into the entire modern understanding of vehicle aerodynamics, both in racing and on public roads. The barn door wing that Ferrari engineers mocked in 1966 is the direct ancestor of every aerodynamic surface on every serious performance vehicle built in the 60 years since. Hall lost the battle. His concept won the war so completely that we've essentially built the entire modern automotive performance world on the foundations he laid in a Texas workshop with slide rules and intuition and a willingness to try something that everyone else thought was ridiculous. The story of what happened to Jim Hall personally after the ban is one that most people who know the 2E's technical legacy have never fully explored. And it matters, because it reveals something important about the relationship between genuine innovation and the institutions that are supposed to celebrate it. Hall didn't retreat to Midland, accept his regulatory defeat gracefully, and spend the rest of his career building conventional race cars. That's not who Jim Hall was. Instead, he did something that in retrospect looks less like stubbornness and more like a systematic, decades-long demonstration that the racing establishment had made a fundamental error in judgment. The pattern that emerged over the following years was almost poetic in its consistency. Every time a new racing series or a new regulatory framework left any ambiguity about movable aerodynamics, Hall found it. Every time the rules created even a small window for aerodynamic innovation that touched on his core concept, Chaparral walks through that window and built something extraordinary. And every single time, without exception, the response from the racing establishment followed the same script. Initial disbelief, followed by competitive panic, followed by regulatory action. Hall didn't just invent the movable wing once. He essentially reinvented it multiple times across multiple decades, and every time the response was the same. The Chaparral 2J arrived in 1970 and took a completely different approach to the downforce problem that was, if anything, even more radical than the movable wing. If you couldn't change the aerodynamic characteristics of surfaces exposed to the airflow, Hall reasoned, what about managing the air underneath the car instead? The 2J used two powerful fans driven by a separate engine, a snowmobile motor mounted in the rear of the car, to actively evacuate air from beneath the vehicle. This created a persistent low-pressure zone under the car that generated enormous downforce independent of vehicle speed. Unlike conventional aerodynamic downforce, which increases with the square velocity, the fan car's downforce was essentially constant regardless of how fast the car was traveling. The implications were staggering. Conventional downforce is most valuable at high speeds and almost non-existent at low speeds. A car with 2,000 pounds of downforce at 150 miles per hour might have barely 200 pounds at 50 miles per hour. The 2J generated substantial downforce at essentially any speed, including in slow corners where conventional aerodynamics provided almost nothing. The car could corner at speeds through slow sections of track that were simply physically impossible for conventional machinery. Skirts running close to the ground sealed the low-pressure zone, and the whole system worked with an efficiency that made even the 2E's advantages look modest. The 2J was banned after a single season. The official reason cited moving parts creating a hazard by throwing debris. The actual reason, transparently obvious to anyone paying attention, was that it was making every other car in the Can-Am series completely uncompetitive. The debris argument was, to put it diplomatically, creative regulatory interpretation. Hall had done it again. Here's what most people don't realize about the 2J's legacy specifically. The ground effect aerodynamics that dominated Formula One from 1977 through 1983, the technology that Colin Chapman developed with the legendary Lotus 78 and 79, and that produced some of the most aerodynamically sophisticated racing cars ever built, was philosophically rooted in the same principle Hall had explored with the 2J. The idea that managing airflow under the car could generate enormous downforce without the drag penalty of wings above the car. Chapman didn't use fans. He used carefully shaped underbody tunnels and sliding skirts to achieve the same low-pressure effect aerodynamically rather than mechanically. But the concept, generating downforce by creating low pressure under the car, was one Hall had proven years earlier. Ground effect Formula One cars became so fast so quickly that they triggered their own regulatory crisis. Cornering speeds reached levels that terrified everyone, drivers, engineers, and governing bodies alike. The lateral G-forces being generated were causing drivers to experience tunnel vision and near blackouts during sustained high-speed corners. The cars were faster than the circuits they were racing on had been designed to accommodate. Ground effect aerodynamics was banned from Formula One in 1983. Another technology restricted because it worked too well. Another page from the Chaparral playbook, just written by different authors. Then came the Chaparral 2K, Hall's entry into IndyCar racing, which won the Indianapolis 500 in 1980. The 2K used a movable side pod configuration that allowed different aerodynamic settings, working right up to the edge of what the regulations permitted. It won the biggest race in American motorsport and was promptly subjected to intense regulatory scrutiny. Hall's fingerprints were all over it. Find the limit of what the rules allow. Build something that exploits that limit completely. Win. Get regulated. The consistency of this pattern across more than 15 years tells you something profound about Jim Hall. He wasn't just a talented engineer who happened to have one brilliant idea. He was someone who had identified a fundamental truth about vehicle dynamics. That variable aerodynamics represent the optimal solution to the conflicting demands of racing performance, and who spent his career finding every possible way to demonstrate that truth within whatever regulatory constraints existed at any given moment. The establishment kept closing the door, and Hall kept finding the window. Look, this persistence matters beyond Hall's personal story because it illustrates something important about how technological progress actually works. The conventional narrative of innovation suggests that good ideas get adopted, refined, and eventually become standard practice. The 2E story suggests something more complicated. Good ideas that threaten existing power structures, existing competitive hierarchies, existing business models, those ideas get resisted, restricted, and sometimes outright prohibited regardless of their technical merit. The question of whether an innovation gets adopted isn't purely about whether it works. It's about whether the institutions with the power to adopt or reject it benefit from doing so. Every established team in 1966 had invested enormous resources in conventional aerodynamic approaches. Their engineers' careers were built on expertise in those approaches. Their competitive advantages were derived from being better than others at those approaches. The 2E didn't just threaten to make their cars slower, it threatened to make their entire accumulated expertise irrelevant. A Ferrari aerodynamicist who had spent 15 years optimizing fixed bodywork had exactly zero transferable advantage when the relevant question became how to design a movable wing control system. Hall's innovation wasn't just technically threatening, it was institutionally threatening. And institutions, it turns out, are very good at protecting themselves. This is where it gets really interesting, because the same dynamic that played out in 1966 racing has repeated itself across virtually every field of technological innovation. The automobile itself was initially resisted by interests tied to horse transportation. Commercial aviation faced resistance from railroad companies with enormous political influence. Digital photography nearly destroyed Kodak, a company that actually invented the digital camera internally in 1975 and then suppressed the technology because it threatened their film business. The pattern of institutions resisting innovations that threaten their existing advantages is so consistent across history that it almost qualifies as a law of organizational behavior. In racing, The institutional resistance to movable aerodynamics has been so successful and so sustained that we've now had nearly 6 decades of some of the most sophisticated engineering minds on Earth spending billions of dollars trying to do with fixed structures what Hall did with movable ones. The cumulative investment in optimizing fixed aerodynamics since 1968 across all racing series globally is genuinely incalculable. Hundreds of teams, thousands of engineers, millions of wind tunnel hours, billions of computational fluid dynamics simulations, all working to solve a problem that Hall solved in principle in a Texas workshop with mechanical linkages. Now, you might be thinking, but surely fixed aerodynamics has gotten so good that it's effectively achieved what movable aerodynamics would have provided anyway? And there's some truth to that argument at the very top levels of the sport. Modern Formula One aerodynamics is so sophisticated that the performance being extracted from fixed structures is extraordinary. But here's the critical distinction. Fixed aerodynamics can never truly optimize for both maximum downforce in corners and minimum drag on straights simultaneously. It can find increasingly sophisticated compromises between those two demands. It cannot eliminate the compromise entirely. Every Formula One car racing today is slower through slow corners than it would be with movable high downforce aerodynamics and slower on the straights than it would be with movable low drag aerodynamics. The entire sport is operating with an artificial performance ceiling imposed by that regulatory restriction. The fastest possible Formula One car, using the best available technology without regulatory restrictions, would have movable aerodynamics. Everyone in Formula One knows this. It's not a secret or a controversial opinion. It's basic physics. And yet the ban remains because the alternative, allowing movable aerodynamics, would trigger exactly the kind of competitive disruption that the 2E caused in 1966. Whichever team solved it first would have an overwhelming advantage. That's unacceptable to a sport that needs competitive racing to generate the commercial value that funds its existence. The DRS system introduced in 2011 represents the sport's uncomfortable acknowledgement of this reality. By allowing a tiny, tightly controlled form of movable aerodynamics specifically to enable overtaking, Formula One essentially admitted that fully optimized fixed aerodynamics produces cars that are too aerodynamically similar in speed to allow organic overtaking. The turbulent air that a leading car's complex aerodynamics produces is so disruptive to the following car's own aerodynamic systems that close racing becomes nearly impossible. DRS is a band-aid applied to a wound that was open when the sport chose fixed aerodynamics over Hall's movable alternative. The 2022 Formula One regulations, which dramatically simplified car aerodynamics to reduce the disruption caused to following cars, represent another attempt to address the same fundamental problem. Simpler aerodynamics means less performance loss when following another car, which means closer racing and more overtaking opportunities. The sport spent 50 years making aerodynamics more and more complex in pursuit of maximum performance, then spent the next decade trying to simplify it to restore racing quality. Hall's movable wing would have solved the following car problem elegantly and automatically. A car following another through turbulent air could simply increase its wing angle to compensate for the reduced aerodynamic efficiency, maintaining its downforce levels despite the disturbed airflow. Instead, the sport chose to ban the solution and has spent 50 years managing the consequences. The financial implications of this regulatory path are almost impossible to fully quantify. Racing teams collectively spend somewhere in the region of $3 to $4 billion annually on aerodynamic development across Formula One alone. That's development of fixed aerodynamic structures, optimizing toward a performance level that is inherently compromised by the fixed structure constraint. Some significant fraction of that investment, nobody can say exactly how much, is essentially compensating for the inefficiency imposed by the movable aerodynamics ban. It's money spent not to go faster than physically possible, but to go as fast as physically possible within an artificial constraint. Jim Hall, who continued to be involved in various motorsport projects through subsequent decades and who remained a respected figure in engineering circles throughout his life, has spoken occasionally about the 2E period with characteristic Texas understatement. He tends to describe the car's reception and subsequent banning in matter-of-fact terms as though it was simply the predictable outcome of building something genuinely better than everything else. There's no bitterness in his recollections, at least none that surfaces publicly. But there is, occasionally, a quiet observation that the problems the racing world spent the next 50 years wrestling with, the following car problem, the downforce versus drag compromise, the cost of aerodynamic development were problems that movable aerodynamics would have managed more elegantly. He's right, and the racing world in its more honest moments knows he's right. The broader cultural impact of the Chaparral 2E is something that almost never gets discussed in the technical histories of the car, and that's a genuine omission because it's arguably as significant as the engineering legacy. The 2E arrived at a specific moment in American cultural history, 1966, when the relationship between technology, expertise, and established authority was being questioned across virtually every domain simultaneously. The civil rights movement was challenging institutional racial authority. The anti-war movement was challenging institutional military authority. The counterculture was challenging institutional social authority. And in a small Texas workshop, a quiet engineer was challenging institutional racing authority with aluminum struts and a movable wing. That parallel isn't just poetic coincidence. It reflects something genuine about the period. The mid-1960s was a moment when the assumption that established institutions were inherently correct, that the way things had always been done represented accumulated wisdom rather than accumulated inertia, was being stress-tested across American society simultaneously. Hall's challenge to racing orthodoxy was quieter and more technically specific than the social upheavals happening around it, but it operated on the same fundamental logic. The people telling you something can't be done, or shouldn't be done, or violates the spirit of how things are supposed to work, might simply be people whose positions of authority depend on things staying the way they are. The drivers who competed in Can-Am racing during the 2E era described the atmosphere of that period with a vividness that suggests it felt genuinely transformative even to people living through it. Can-Am in the mid to late 1960s was arguably the most exciting racing series in the world. It combined the financial resources of major manufacturers with the regulatory freedom to try virtually anything, the star power of the best drivers from Formula One and sports car racing, and the genuine danger that made every race feel consequential. It was American racing at its most ambitious and its most spectacular. The 2E fit that context almost perfectly. It was American in its origin, built in Texas by a Texas engineer using American engineering resources and American manufacturing ingenuity. It was ambitious in its conception, not satisfied with doing what everyone else was doing slightly better, but determined to do something categorically different. And it was spectacular in its execution, visually dramatic in a way that communicated its revolutionary nature even to spectators who had no technical understanding of what they were watching. You didn't need to understand aerodynamics to understand that something different was happening when Phil Hill drove the 2E. You just needed eyes. Here's the thing about spectacle in racing. It matters in ways that pure performance metrics don't capture. Racing has always been entertainment as well as competition. And the most memorable moments in the sport's history tend to be the ones where something visually extraordinary happened that made people feel they were witnessing something beyond ordinary experience. The 2E provided that feeling in abundance, the wing moving visibly as Hill braked and accelerated, the car taking lines that looked physically wrong at the speeds involved, the lap times that made experienced people question their stopwatches. These were the ingredients of genuine spectacle, of the feeling that you were watching history being made. The photographs and footage from the 2E's competitive appearances have an almost timeless quality that the best racing documentation always carries. There's something about the image of that white car with its enormous wing, low and aggressive against the track surface, that communicates the car's essential nature immediately and completely. It looks fast. It looks radical. It looks like something from a future that the present wasn't quite ready for, which is, of course, exactly what it was. Now, you might be thinking about the safety dimension of all this because any honest discussion of 1960s racing has to address the fact that it was extraordinarily, almost incomprehensibly dangerous by modern standards. Drivers were dying at a rate that would be completely unacceptable today. The 1966 and 1967 seasons that bracketed the 2E's competitive career saw multiple fatalities in major international racing. The sport was simultaneously at its most innovative and its most lethal, and those two facts were not unrelated. The movable wing actually addressed some safety concerns that conventional aerodynamics of the era did not. The aerodynamic braking effect of the wing at maximum angle meant the car could decelerate more rapidly and more controllably than a conventional car with equivalent mechanical braking. Brake temperatures, which in the era of relatively primitive brake technology were a genuine safety concern, were substantially lower on the 2E than on comparable cars because the wing was doing significant deceleration work that would otherwise have gone entirely through the brakes. Overheated, faded brakes were a contributing factor in multiple serious accidents during this period. The 2E's approach to deceleration was, in this specific respect, genuinely safer. The downforce itself also contributed to safety in the high-speed corners where the most catastrophic accidents tended to occur. A car with 500 pounds of additional rear downforce is significantly less likely to lose rear grip suddenly and unpredictably at high speed than a car with no aerodynamic assistance. The 2E's behavior in high-speed corners was more predictable and more controllable than conventional cars of the era, not less. The narrative that somehow the movable wing was dangerous is not well supported by the actual engineering analysis of how the system worked. The genuine safety concern with the 2E was more subtle and more interesting than the simple danger narrative suggests. The car's performance envelope was so far beyond anything else that existed that it raised questions about driver preparation and circuit infrastructure. Tracks that had been designed with certain speed expectations built into their runoff areas and barrier placements were now being navigated at speeds those design assumptions hadn't anticipated. The danger wasn't really in the movable wing itself. It was in the gap between what the car could do and what the surrounding environment had been built to accommodate. This is a pattern that repeats consistently throughout racing history. Whenever a genuinely transformative performance advance occurs, the technology outpaces the infrastructure. The solution, which modern racing has largely adopted, is to upgrade the infrastructure. Bigger runoff areas, better barriers, improved medical facilities, revised circuit designs that accommodate higher speeds safely. The alternative solution, which the 2E's era chose, is to restrict the technology. Both approaches address the immediate concern, but they have opposite implications for long-term progress. The drivers of the 2E era were, by any reasonable standard, operating at the absolute frontier of human courage and skill. These were people who got into racing cars in the 1960s fully aware that their sport was killing their colleagues at regular intervals, and who chose to continue anyway. Their relationship with risk was calibrated completely differently from how modern society thinks about acceptable danger. When Phil Hill described the 2E as giving him confidence he'd never felt in another car, he was saying something meaningful against that backdrop. This was a man who had raced the most dangerous cars of the most dangerous era. The movable wing made him feel safer, not more exposed. The legacy question that most fascinates the engineering community, the one that gets debated in technical circles and occasionally surfaces in academic papers, is what racing would look like today if the movable wing had never been banned. This is genuinely difficult to reason about because the chain of consequences extends so far and branches so many times that confident prediction becomes impossible. But certain things seem reasonably likely. Aerodynamic development costs would almost certainly be lower, not higher. The reason modern racing aerodynamics is so extraordinarily expensive is that fixed structures have to be optimized with incredible precision to extract maximum performance. The margins between good and great fixed aerodynamics are tiny, which means the investment required to find those margins is enormous. Movable aerodynamics, which can adapt to conditions rather than being frozen at a single compromise point, would likely have shifted competitive advantage away from those tiny margins and toward the broader system design and control strategy. Different skills, different investments, potentially lower total cost. Racing would almost certainly be closer. The following car problem, which has plagued Formula One particularly for decades and which has driven enormous regulatory effort and expense, would be substantially mitigated by movable aerodynamics. A car following through turbulent air could compensate by adjusting its aerodynamic configuration. The performance lost from running in another car's wake would be smaller and more manageable. Overtaking would be more organic and less dependent on regulatory mechanisms like DRS. The technology transfer to road cars would have happened faster and more completely. Movable aerodynamics on road cars, which is now appearing on the most advanced hypercars, would have been developed and refined decades earlier if racing had continued pushing the technology rather than banning it. The Bugatti Chiron's air brake and the McLaren P1's active wing are technologies that might have been appearing on mid-range performance cars by the 1990s if Hall's concept had been allowed to develop through racing competition. This is where it gets really interesting from a pure engineering philosophy perspective. The ban on movable aerodynamics in racing represents one of the clearest examples in technological history of a performance optimization that was available, proven, and then deliberately rejected in favor of a constrained alternative. In most fields of engineering, this would be considered a catastrophic failure of rational decision-making. You don't ban the better solution and mandate the worse one. Except in racing, where the competitive and commercial dynamics create pressures that override pure engineering logic. The result is a sport that has spent nearly 6 decades and hundreds of billions of dollars cumulatively optimizing within an artificial constraint while the unconstrained solution was known and available from the beginning. Every Formula One lap time set since 1968 has been set by a car that is inherently slower than it could be because of a regulatory decision made in response to one white car winning too convincingly in 1966. Jim Hall's contribution to automotive engineering is honored in the appropriate places. The Chaparral 2E is displayed in museums. Hall himself has received lifetime achievement recognition from various motorsport organizations. The technical histories acknowledge his innovations, but the full weight of what he accomplished and what the sport chose to do with it deserves more prominent recognition than it typically receives. He didn't just build a faster car. He solved the fundamental problem in vehicle dynamics so completely that the solution had to be prohibited to preserve competitive balance. That's not just an engineering achievement. That's a category of achievement that barely has a name. The movable wing proved that the optimal race car is not a fixed object optimized for average conditions, but an adaptive system that responds to varying demands in real time. That insight is now embedded in virtually every advanced engineering system in existence, from aircraft flight control computers to active suspension systems to electronic stability control in ordinary passenger cars. The principle Hall demonstrated with mechanical linkages and bronze bushings in 1966 is now implemented digitally in billions of vehicles worldwide. He was right. The world caught up. Racing, uniquely, chose not to. The question that lingers over everything, the one that serious students of motorsport history keep returning to, is deceptively simple. Was banning the movable wing the right decision? Not technically, not commercially, morally. Was it right to prohibit a technology because it worked too well? The instinctive answer for most people is yes, of course. Racing needs competition. If one team has an overwhelming advantage, it's not really racing anymore. The ban preserved the sport's competitive integrity and allowed multiple teams to remain relevant. That's a legitimate argument, and it deserves to be taken seriously rather than dismissed. But here's the thing. That argument contains an assumption that rarely gets examined. It assumes that the purpose of racing regulations is to maintain competitive balance. And if that's true, then banning the 2E was rational and correct. But racing has never actually operated on that principle consistently. Teams with larger budgets have always had advantages. Manufacturers with more resources have always been able to develop superior engines, better materials, more sophisticated chassis. The entire history of racing is a history of resource advantages, translating into performance advantages. Nobody banned Ferrari for having more money than privateer teams. Nobody banned Lotus for being more innovative than their competitors in chassis design. The 2E was banned not because it created an advantage, but because it created an advantage that was too obvious, too dramatic, and too immediate to be absorbed gradually into the competitive landscape. A new engine that's slightly more powerful can be copied over 1 or 2 development cycles. A completely novel aerodynamic system that requires entirely different engineering expertise and manufacturing capabilities is a different category of challenge. The 2E's advantage was so large and so rapidly established that the copying process would have taken years, during which competitive racing would have been essentially impossible. Look, there's a genuine tension here that doesn't resolve cleanly. Racing needs innovation to remain relevant and to justify its enormous costs through technology transfer and public interest. But racing also needs competition to function as entertainment and to maintain the commercial relationships that fund innovation. The 2E pushed those two requirements into direct conflict in a way that the sport wasn't equipped to manage. The resolution, banning the innovation, preserved competition at the cost of progress. Whether that trade-off was correct depends entirely on what you believe racing is fundamentally for. Here's what most people don't realize about the long-term consequence of that choice. By establishing the precedent that sufficiently dominant innovations would be banned, racing sent a signal to engineers everywhere about what kind of thinking was welcome. Incremental improvements within established frameworks? Good. Categorical innovations that redefine the performance envelope? Dangerous. The most creative engineering minds in the world received a clear message that truly revolutionary ideas would be regulated out of existence the moment they proved too effective. The chilling effect on radical innovation in racing has been real and lasting, even if it's impossible to measure precisely. The engineers who might have followed Hall's path, who might have found the next categorical innovation in vehicle dynamics, had strong incentives to redirect their creativity toward incremental optimization instead. The result is a sport that is extraordinarily good at doing what it already knows how to do and structurally resistant to doing something genuinely new. Formula One teams employ some of the most talented technical minds on Earth and spend extraordinary sums to find performance gains measured in hundredths of seconds. The returns on that investment in terms of pure performance advancement are diminishing in ways that Hall's approach would never have allowed. This is where the 2E story connects to something much larger than racing. We live in a world that constantly celebrates innovation rhetorically while frequently resisting it institutionally. The technologies that have most profoundly changed human experience, from the printing press to the internet, have almost universally faced institutional resistance from entities whose power depended on the status quo they threatened. Racing's response to the 2E is a compact, clearly documented example of exactly this pattern, which is part of why it remains so worth studying 60 years later. The movable wing didn't fail. It succeeded so completely that failure was imposed on it from outside. That distinction matters enormously. When we look at technologies that didn't change the world and try to understand why, we need to ask not just whether they worked, but whether the institutions with the power to adopt or restrict them had incentives to do so. The 2E worked. It was restricted anyway. The lesson is uncomfortable but important. Jim Hall never stopped engineering, never stopped finding the edges of what regulations permitted, never stopped believing that the right answer to the corner versus straight compromise was a system that could adapt rather than a structure frozen in compromise. That persistence, maintained across decades and multiple racing categories, is itself a form of argument. It's Hall demonstrating through his career that the insight behind the 2E wasn't a lucky accident, but a genuine engineering truth that kept reasserting itself regardless of what the rulebook said. Every time you watch a modern hypercar deploy its active aerodynamics, adjusting its wings and flaps in real time to optimize performance for changing conditions, you're watching Hall's vision finally finding the space to exist outside the regulatory constraints that prohibited it in racing. The road car world, which faces no such constraints, has embraced movable aerodynamics completely. The fastest, most sophisticated road cars on the planet all use it. The fastest, most sophisticated racing cars on the planet are still prohibited from using it. That gap between what road cars can do and what racing cars are allowed to do, a gap that exists on this specific dimension because of a decision made in response to one white car from Texas in 1966, is perhaps the 2E's most lasting and most ironic legacy. Racing, which exists partly to push automotive technology forward, banned a technology that the road car world eventually adopted anyway. The detour just took 60 years. The Chaparral 2E showed us exactly how fast a race car could go when the aerodynamics worked with the driver instead of against them. We decided we weren't ready for that. The question worth asking as active aerodynamics becomes standard on the world's most advanced road cars is whether we're ready now. Drop your answer in the comments below, and don't forget to subscribe to Legacy Motoring for more stories about the engineering brilliance that changed everything.